Earth exists. That much is obvious. But existence and world are not the same thing. For most of its early history, Earth wasn't a world. It was an unstable configuration that kept resetting before anything could last. The conditions that allow a planet to persist long enough to sustain systems weren't guaranteed. They had to survive repeated physical stress without collapsing. Earth nearly didn't make it. We're looking at a planet roughly 4.5 billion years ago. In the first few 100 million years after its formation. This period, the Hadean, gets treated in most accounts as a prelude. A violent but temporary phase before the real Earth began. That framing misses the actual problem. During this time, Earth wasn't waiting to become stable. It was failing to hold conditions long enough for anything to build on what came before. Every process that began got interrupted. The surface wasn't cooling into something durable. It was cycling between molten and fractured states. The atmosphere wasn't thickening into a protective layer. It was being stripped away faster than it could accumulate. This wasn't a transition. It was a dominant state. What we call Earth today only exists because something shifted. Not because the planet was destined to stabilize, but because certain physical conditions managed to persist slightly longer than they had before. The question isn't why Earth became a world. It's how anything managed to last. Here's where the distinction becomes physical. A planet can exist without being a world. Existence only requires mass, gravity, and orbital position. A world requires something more, the ability to maintain conditions that don't immediately reset. Early Earth had mass. It had gravity. It had a position in the solar system's habitable zone. But none of that guaranteed persistence. The surface was molten for extended periods, not as a one-time event, but as a recurring condition. When crust began to form, it didn't stay. It fractured under thermal stress or got reabsorbed into the mantle. Liquid water, if it existed at all, couldn't remain on the surface long enough to interact with rock in stable ways. Atmospheric gases accumulated, then got stripped by solar wind or impacts before they could create pressure equilibrium. Each of these isn't a setback. It's a reset. If you're aligning with this kind of analysis, the kind that doesn't treat Earth's survival as a given, the like button reflects that. It's not approval. It's recognition that this approach matters. The planet kept cycling. It didn't sustain. And without sustained conditions, there's no chemical continuity. No thermal regulation, no accumulation of the processes that would eventually allow complex systems to develop. Persistence is the threshold. Early Earth repeatedly fell short of it. So what kept failing? Start with heat. Earth formed from accretion, smaller bodies colliding and merging. That process released enormous kinetic energy, most of which converted to heat. The result was a magma ocean, a planet-wide layer of molten rock hundreds of kilometers deep. For a magma ocean to cool, heat has to radiate into space faster than new heat gets generated from radioactive decay in the interior. But cooling isn't a smooth process. As the surface begins to solidify, it forms an insulating layer that slows radiative loss. Heat builds up underneath. The crust fractures. Molten material breaks through. The cycle starts again. This isn't speculative. We see the geochemical signature of repeated melting and solidification in the oldest zircon crystals. These crystals, some over 4.4 billion years old, show isotopic ratios that only form when liquid water interacts with cooling rock. But they also show signs of being reheated. Sometimes multiple times. The conditions that allowed them to form didn't persist. They got interrupted. Now add impacts. During the late heavy bombardment, Earth's surface was being struck by planetesimals and asteroids at rates far higher than today. Each large impact delivered enough energy to vaporize surface rock and eject material into space. Smaller impacts were constant. They didn't just crater the surface. They reset the thermal state of entire regions. If an atmosphere had started to build, a major impact could strip it partially or completely. If liquid water had pooled in basins, the same impact could boil it off or disperse it as vapor. The planet wasn't moving toward stability. It was being forced back to starting conditions. Then there's the magnetic field. Earth's magnetic field today shields the atmosphere from solar wind. Without it, charged particles from the sun strip lighter gases directly into space. But generating a magnetic field requires a convecting liquid iron core. Early Earth's core was still differentiating, heavy metals sinking, lighter silicates rising. Until that process stabilized, the dynamo effect couldn't sustain itself. The field flickered. It weakened. It failed. Each of these processes, thermal regulation, atmospheric retention, magnetic shielding, had to work simultaneously for the planet to hold together as more than just mass in orbit. None of them worked reliably. Each failed repeatedly. And when one failed, it made the others more likely to fail. The planet kept trying. It didn't keep succeeding. If the method here, looking at failure as the informative state, not the exception, feels like the approach you want to keep encountering, subscribing reflects that alignment. It's not about following future videos. It's about continuing to think this way. At some point, the resets became less frequent. Not because the processes stopped being violent. Not because external disruptions ended. But because certain conditions began lasting longer before they got interrupted. The magma ocean cooled unevenly. Some regions solidified faster than others, creating the first stable crust. These patches didn't cover the planet. But they persisted long enough for minerals to differentiate. And for water vapor in the atmosphere to condense without immediately re-evaporating. When impacts occurred, they no longer vaporized the entire surface. They damaged local regions. The rest stayed intact. The core's differentiation progressed as the liquid iron layer thickened. And its convection became more regular, the magnetic field strengthened. It didn't become constant. But it stopped collapsing completely. That meant the atmosphere could begin accumulating without losing its lighter components at catastrophic rates. Water, likely delivered by comets, and water-rich asteroids, started pooling on the surface. Not as stable oceans, but as transient bodies that evaporated and reformed. Over time, some of these bodies lasted long enough to chemically interact with the cooling crust. That interaction created the first clays, the first carbonates. Materials that could only form when water stayed in contact with rock for extended periods. None of this represents a solution. It represents a reduction in instability. The planet didn't become stable. It became slightly less unstable. And that difference, marginal as it was, allowed processes to build on themselves instead of starting over. We don't know the exact sequence. The geologic record from the Hadean is almost entirely missing. Most of the rock that formed during that time has been subducted, melted, or eroded beyond recognition. What we have are fragments, zircon crystals, isotopic signatures in younger rocks, impact crater distributions on the Moon that we extrapolate back to Earth. Models of early planetary cooling are constrained by physics, but the specific timing depends on variables we can't measure directly, the exact rate of heat loss, The composition of the early atmosphere, the frequency and energy of impacts in the first 500 million years. We can estimate. We can't verify. There's also uncertainty about when liquid water became persistent. Some zircon evidence suggests it existed as early as 4.4 billion years ago. Other models argue the surface remained too hot for stable liquid water until 4.0 billion years ago or later. Both interpretations are consistent with parts of the available data. Neither can be confirmed without direct samples from that period. The magnetic field's history is similarly incomplete. Paleomagnetic data from ancient rocks shows the field existed by 3.5 billion years ago. Whether it existed earlier and whether it was continuous or intermittent remains unresolved. These aren't gaps we can fill with speculation. They're limits. And when unresolved ideas like these get shared, they gain clarity, not through agreement, but through external challenge, through the friction of people disagreeing about what the evidence actually supports. What we can say is this: Earth transitioned from a state where persistence was rare to a state where it became frequent enough to matter. The mechanisms are understood in broad terms. The specifics are not. So Earth managed to persist. Eventually. But the question doesn't stop there. If Earth came that close to failing, if it spent hundreds of millions of years resetting instead of building, then it raises a larger problem. Was Earth the first configuration in this region of space to cross the persistence threshold? Or were there others that tried and didn't make it? The solar system didn't form as a finished structure. It formed as a series of attempts. Some of those attempts lasted. Most didn't. If Earth nearly wasn't a world, then we have to ask what happened to the configurations that came before it. The ones that formed, destabilized, and disappeared before anything could build on them. That tension, the realization that persistence isn't guaranteed even when conditions look favorable, doesn't resolve here. If that discomfort feels unfinished, comments are where it continues. Not to close the question, but to sharpen it.